So let me briefly remind you the frequent problem. Okay, so remember that. So okay, let's delete this distinct problem because we are going to go back later. So remember that we have a streamline A1, A2, like AM. This is a really long sequence, right? Okay, and then we assume that these are from excuse me, universe of n elements. Okay. And here we want to output this y. Output the set okay, so here k is a given parameter, right? And remember that fj is the frequency of j, right? Namely, how many times j appears in the stream. Okay, so do you remember the algorithm? This Mishra-Grimes algorithm. So I'm not going to go over the algorithm, but let me just state what we obtained as a result. Okay, and how we are going to improve the result, right? So we show that Mishra Grimes. It just finds it. It gives estimates. This we put head right to emphasize that it's an estimation. So fj head is the estimation of fj. Okay, so it outputs such that fj. Remember, this is always underestimate, right, of actual frequency, right? But then we also had this guarantee, right? So it was not okay. This was guaranteed. Okay, so what does this mean, right? So it's an estimation. So, but if you want to solve this problem, right, we have to make another pass. So, remember that this algorithm like maintains basically k, counters, right? Actually, n plus k minus 1 counters. Once you have like k counters and you just decrease like count of all those. So to maintain, you always have n most k minus 1 counters. Okay, by doing that, the idea was that hey, we decrease all the counters by n most m over k times it. Okay, therefore, we may underestimate, but not too much. That was the idea. Okay. Anyway, this Mishra-Grimes algorithm, this is one pass, right? Okay. But then let's make some simple observation here. So what I know is that, well, okay, let's define this, right? Let's call this set S. Okay, these are the set of elements that appear many times, namely more than m over k times. Okay. What I know is that if an element is a high frequency element, okay, then the estimate would be strictly positive. Okay, so it means that the frequency should be at least m over k, and therefore the estimation will be at least it's greater than 0. Make sense? Okay, so so because of this, by making another pass on the item j such that fj, right, So, okay, so any element y in S y will have a strict possible estimate. So we'll make another pass, the second pass on the string, and then then we can because we D is phi. By the way, here D. Here the number of such elements y will be at most k minus 1 or k, doesn't matter. Okay? So therefore, it's k small typically. So by counting the elements, these elements y exactly, we can see if fj is big or not, and therefore we can find the s by making another pass. Okay, any questions about this? Just to make sure here, this is important, right? So I mean, do you see why we must make a second pass here? Because if the estimate is positive, right, it doesn't necessarily mean that the tree frequency is actually more than m/k. So we need to actually verify. Okay, but all we know is that by running Mistral-Grice algorithm, we can identify only a few elements that can possibly have high frequency. So in the second pass, we actually verify that some of them actually have a high frequencies. Right? That's why we make two passes. So the whole algorithm, it's a two-pass algorithm. Okay. If you want to estimate, yeah. So to solve this problem, you need to make two passes. Okay, make sense? Okay, good. So yeah, let's move to chapter 4, and then I'll come back to chapter 3 and 4. Excuse me, chapter 2 and 3. So here, yeah, we have a similar problem here. We want to, some frequent element we want to estimate this fj hat, right? That's the same goal. But now in chapter 4, we want to have a one-pass algorithm. It's a huge deal because you don't have to repeat the whole thing twice, just make one pass. This algorithm, the first algorithm we are going to see is a count. It's called a count sketch. This is a basic version. Okay, we are going to make it stronger by repeating this algorithm. But let's first focus on the basic algorithm, because this basic algorithm has the key ideas. Okay. So I kind of simplified the presentation here. If you see the lecture notes, you will see this J comma C. What this means that J appears C times N. So instead of you seeing C copies of J, I mean it can be more compact, right? So this token means that hey, you have a C copies of J. But let's ignore that, okay? So let's think about the vanilla string model where we see one element each time. So I'm going to just remove this C. Okay, but anyway, if you see the C in the lecture note, it means the count of J. So let's remove this. Okay. So it's very kind of a simple algorithm, but kind of mysterious here, right? So we're going to use two hash functions. The first hash function, both hash functions are we sample both hash functions from two universal hash family. Remember that, it means that they kind of guarantees pairwise independence. I'm going to explain again, but anyway, we'll have two hash functions. The first one has, both have the same domain, right? N is the universe, right? From the universe to K. What is K? K is the hash table size. So let me visualize this because it's I think I can delete this. Just I come back to this. I think I can delete this. So let's delete this. This is how I visualize the algorithm, okay? So I think this is kind of a right interpretation. So what we have here? So we have a K, we create K slots here, right? This table. So of course C stands for count here, okay? So what's interesting is the following. K size is equals 3 over epsilon squared, but let's ignore that, okay? So assume that this is some constant size that depends on the actress parameter epsilon. That's not a big deal, but here, what's really interesting is this. So, okay. Probably it'll be kind of a, so let's, so it's remember that N is the universe size, okay? So I'm going to draw bar to to describe its to visualize its size. Frequency. So like f1, like 1 appears f1 times it. So if it's longer means that it appears more, right? So you still understand why I'm doing this. So and then maybe 2 appears like less, so it's f2 here. F3 appears a lot here. Like let's focus on some J here, some element J. Okay. So say typically we are interested in estimating the frequency of the high frequency items. Okay. So let's say that J has high frequency, so that's why it's long. Okay. Maybe let's make it even lower. And probably I want to actually use different color because this is important. Okay, then now we are going to map. We are going to place these bars right here. Okay, so why? So I may like add the plus side or minus side. Okay, what's happening is this. So note that here for every element right, we have hash function. The function right will map every element to either -1 to 1. That's what second function does, right? So the first function h, right? They'll map, okay? They'll map this to some position. Like for now, think of it as a random function, okay? It's not we are going to see, where the two universal pairwise independence plays a role. But for now, it's to gain intuition. Let's assume that this is kind of random like mapping. I mean, at the high level, that's what the hash function does, right? So this is mapped to this slot. Okay, and then furthermore, this done by what? H. So this is also, you can think of this also H of J, right? Let's right? And then the next function G will determine its sign. It can be either +1 or -1. Okay. Okay. Suppose this it was assigned to -1, right? So I'm gonna place these two here. This is Fj, and this is G. Gj is -1. That's why I put this bar in the negative side. Okay. So, okay. Now let's think about the. Okay, but for now, suppose. Okay, for now, let's ignore like these guys. Imagine that you only have like this J element J. Okay. Then you want to check that actually the algorithm outputs the correct answer, right? So. Actually, let me for a second talk about other elements. So maybe this F1, right? Maybe this guy will be assigned like here. Maybe this guy was assigned to the same slot, F1, because G1 is 1, so it's it's positive side. And F2, this guy maybe will assign to also this maybe the same goes to same slot, but again this time it's goes to negative side. Okay, and this guys go to maybe goes to some positive side. Because it was signed there, +1. Okay. So actually, So what do I mean? See, you first need to understand why this makes sense based on the algorithm, right? So we are going to see. So whenever we see element J, right, we are going to add G of J, right? So here G of J is -1, right? We are going to see J, Fj times. So we are adding Fj, we are J -1 Fj times, right? That's why I direct this Fj on the negative side. Okay? But there can be, but look, this table is much smaller than the actual this number of elements, right? Therefore, like many like elements will map to same slot. For example, like this element 1, element 2, they'll go to same slot at J. Okay? And some will go to the positive side, some will go to the negative side. Okay? But again, to gain intuition, like imagine that this is like a high frequency element. High frequency elements, right? But then the others are kind of again some like low frequency elements. Okay, then what happens? Okay, so what do we do right here? So think about this. We have Fj. What do we output here, right? So we output. So as an estimator of Fj, we output G of J, right? And plus the counter. So here Fj, right? We added Fj times this, right? Okay, and then the other guys, so maybe G2, G1. Suppose G1 and 1 element 2 both went to this slot. And then it'll be F1, G2, F2. I mean, there can be other elements, right? Okay, but what's good here, right? So this, if you look at this, right, GJ, right? And this is always 1, right? Because g of j can take a value either 1 or -1. It's squared, right? This is always 1, right? So you'll get fj, right? If you don't have other elements. But what's happening, right? So so the assumption is that we have a high frequency item here, right? But the other items are like low frequency items. We just took an intuition, right? But these items where we go to either to right side or left side, it's plus side or minus side, right? But basically they'll cancel off. Okay, so these are kind of noisy in some sense. And so you get fj. Does it make sense? Or why do this? Like it's a very clever algorithm. So and we're going to show that actually this is very important. So we're going to show that fj had, right? Our estimations expectation is fj, which means that it's unbiased estimator. Because these are this g1 can be either +1 or -1, so an expectation will be 0, right? And because we have to we have separated this gj and g1, right? Because we need independence between j and 1. This is where we are going to use a pairwise independence, 2 universal family. Okay, this is kind of a high level overview. Does it make sense? Okay, of course, we need to like here, like we assume that hey, we assume that it's kind of random function, but like to make to use compact hash functions, right? We'll have to use the 2 universal hash family, the properties, not random, complete randomness. Any questions so far? This is just intuition so far. Yes.
So the goal is to estimate the frequency for
Fig-
each g, right?
That's right. For every fj, we want to estimate frequency. Yeah. Any questions so far? I think it's actually the most important thing is to understand why this works, right? I mean, you'll forget mathematics behind, right? But why, like we're doing discounting, why they're doing this, +1 -1, right? This is my interpretation.
So
Yes.
So how to define h? I mean,
H.
Is it up to us or no?
We're going to sample. So we covered the universal hash family. So we are going to select choose H. So we define some hash family, and then from hash family we sample a function. So H is a random function in the sense. Okay, and because we are going to use only a small hash function, hash family, so to remember the hash function, we can use only small number of bits. Okay. Any questions so far about the algorithm, intuition? Before going to math. It's good. Okay, but math is math, so you got to do the work, right? So I think I can use this part. So let's do it. Okay, we are going to make two important, we are going to show two important things here. The first one is, as I already said here. Okay, so actually let's define this. Let x be, so fix a, right? Fix some element a, and we want to estimate its frequency. Okay, so it's a random variable because our algorithm is randomized algorithm. So I want to see what's its value, right? So because I mean, as we argued, as we said, kind of observed at the high level, we are going to show that So again, the first claim, I mean, we are going to show these two claims, and we are going to see what these two claims imply together. The first claim means that this is an unbiased estimator. It's very important. It's very important. So, like, yes, you're, if the expectation is the same, the expectation is the same as true value, then which means that if you repeat this by, eventually you'll get, you'll converge it, right, to the right value, okay? But then now you want to say, and now why do you care about variance? Because if the variance is high, then it can deviate from the expectation a lot, right? Therefore, if the variance is small, then you will need to repeat this fewer times, okay? And also you will see like how worse can it be? How bad can it be, right? So we are going to study these two and make some nice claims out of this. Okay? So I'm going to explain what these are, what this means, but let's not worry about that for now. No, actually, let's first, let me first explain what this means and what these two imply together. Okay, together these are the result. Okay, so I'm going to claim that if we have these two properties, then we'll have okay, what does this mean? So this common notation. This means the L2 norm. Okay, so which means that f1 square, f2 square plus fn squared by and take the square root. Okay, so if you take it the square on both sides, right, then this will go away. So you'll get this, right? So what this means is this. So, okay, this means, right, that this is the same, but you just want to take off fa squared. Okay, so like sometimes people often use this notation, right? So this. This is common notation. What this means that, okay, let's get all the elements, right? Entries except the A. Okay, just take it off. That's it. So this is the exactly this one. So this is some quantity, like it's L2 quantity, and the probability that our estimator estimate deviate from the expectation, right, by more than this much is at most 1/3. That's what I want to show. Okay. So
Excuse me.
yes,
First expression should be f minus fa, right?
this one. Yeah, minus a.
Minus a? Or
Minus a.
Oh.
It's notation, just notation.
Oh,
That's a-
minus a.
Yeah, minus a, because it means that we are just taking off a
Oh.
in the summation. Okay. So I want to make one comment here. So this. Okay, remember that in Mishra-Grice algorithm, we get this guarantee, right? F was guaranteed. This Mr. Kreis algorithm. So, but how do we compare this algorithm to this, right? Okay, let me explain how we compare this. So obviously, by the way, this L1 norm, right? This means it's just the summation of all entries. So it's F1 plus F2 plus everything, right? So this will be just M, right? The number, the stream length. Okay? And then, like, what is this? So L2 norm. So, like, it is well known that L2 norm is always smaller than L1 norm. So basically, M is like L1 norm, right? Here, like L1 norm divided by K. Okay. So yeah. Okay, so like imagine that this is like L1 norm here, right? And to make it comparable, right? So you need to set epsilon, right? Epsilon to 1 over K. Okay? So then it'll be comparable. I mean, if it is L1 norm, right? But we have L2 norm. So typically L2 norm is better. So actually this to make it equal, like if only one element has a frequency, like for example like a 1000, right? Then you see that both are equal, right? But however, like they are all equally distributed, right? Like say like univector, right? Then you'll see that this will become M, this will become square root M, right? So basically, if they're like if the frequencies are kind of are spread out over elements, L2 norm is much better than L1 norm. So it's a yeah. So I mean it is pros and cons here because this deterministic algorithm. So you have this is always guaranteed, right? But if you're okay with randomization, if you believe that the frequencies are spread over items, elements, then probably this algorithm, counting sketch algorithm, is better than this requires algorithm. Make sense? Okay. Good. So because I explained this, let me just delete this again to save space. Okay. To verify this is kind of easy, but let me just do this. So what do we do? Let's take a square on both sides. Okay? So it'll be FA. The same as with this, right? Okay, we took square, right? So this is obviously non-negative. Okay, so we can apply Markov inequality. Actually, it's basically Chebyshev inequality. Okay, so this will be bounded by expectation of this divided by epsilon squared f minus a. You see, this is the definition of variance, right? The expectation of deviation, right? Squared. So this is variance. So okay. Anyway, so this is variance. So I can just plug in, right? So this variance is what? I just plug in here. By the way, this was just if I should write this. and then because we set k equal to 3 over epsilon squared, this will be 1/3. So again, the math is not very important. Okay, so the point is that like we want to see how much how unlikely our estimate can deviate from expectation, right? To do that, we need to understand the variance. So once we know the expectation and the variance, we can bound it. That's what we're doing here. Okay. Any questions so far here? Do you remember this? No? No? Okay, so let me remind you. So if you have like suppose you want, okay, so say y is non-negative, okay? Then you want to see, you want bounded, it's tail bounded. So namely, okay, what's the probability that say y deviate, y is like more than c, okay? And this is nothing but right? This is Mark. It's like the proof is like really one line, right? Suppose this is not the case, right? That means that like with high probability, you can have high value. Therefore, the expectation will exceed E of y. Okay, that was the proof of Markov inequality, right? And we use this to derive a Chebyshev inequality, and also derive channel bounds. Okay, but we mostly use the Chebyshev inequality. That only uses expectation and variance. So what I here did is that, hey, just take square of both sides, and then apply Markov inequality. Okay. Any questions so far? So what it is, right? This is the expectation of this, and this is the right hand side, the bound, right? Threshold. So calculation goes. Okay, so now I can talk about a little more here. And somehow I lost the page, but I think I can do it on the fly. So okay, so what do we have here? We have interesting. I guess I lost that. I apologize. I had one page lecture note. My handwriting, but I lost it. But I can do it on the fly. So okay. So what I'm going to do is that I'm going to summarize it. Okay. So I haven't proved this. Okay. I'm going to prove this. But before proving these two main properties, expectation and variance, I want to see, I want to kind of summarize the, the how much memory we use, and then what's the success probability and so forth. Okay, because clearly this is one pass algorithm. Right? We just read through the whole stream, and whenever we see J, like we add J, right, to the entry of the table that is mapped by this hash function H. Okay, so we just need to do once, and at the day we just when he asked about A, what about A's frequency, we just output this. No need to make another pass. Clearly one pass algorithm, right? Agree? Okay, now let's think about this memory usage. Okay, how much memory do we use? So, like we have two universal hash functions, right? This universe size. Remember that we need to use basically overload times the universe size. That's how much memory you need to use to store the hash function. So it'll be overlog n. I have two functions right here, so it's an overlog n still. Okay. And what else? Did I do this something? Okay. I don't know why. So it's just yeah, somehow the print out just the print everything. Okay. Good. So from here, hash functions we get log n. I'm ignoring all notation for now. Okay. And then we are going to have k counters, right? For each entry we have a counter, and the count can be as big as m, because m is the the total number of elements, right? The string length. So we'll have a k times mos log m, right? That's the memory usage. So but see, k is what? Like 3 over epsilon squared, right? So this is memory usage. Okay. Then what about the approximation guarantee here? So this, right? The probability that FA our estimate deviates from more than this is that's this way. So yeah, we succeed with this probability. This is our success probability, right? This is our the delta probability, right? We use, right? This is additive guarantee, right? So we found how much it can deviate, right, from expectation, the true frequency, right, by this much. And then this is success probability. We may fail, but with 2/3 chance we'll succeed at least, right? Okay, so I'm going to briefly mention this tree, the median tree. So what does it do? Oh, I did actually here. So what do is this here? Basically, repeat this algorithm. Actually, repeat is a wrong choice. So I'm going to say that run the same algorithm. So we're going to run the same algorithm this many copies. Okay? So what it means that, okay, so at the end of the day, we are going to estimate, okay, for like FA, we are going to get like, this, let's call this T, right? We are going to get a T estimates because we are running the same algorithm, right? T copies. Okay? Yes?
Inside T is a log of 1 over G.
What over log delta, I'm sorry. So there, okay, so let's do this. So we want to we want to have a 1 minus delta success probability. Okay, this is your success probability parameter. So if you want to make it small, then you have to run more copies. Okay, which means that for each algorithm, for each copy running, then you have to use different hash functions, right? Make sense? Okay. Then what we do? Return median we return the median of these T numbers, right, as our solution estimate. This is called the median tree. Okay? Is that clear here, right? And then now you see, now we like, let's see why. Okay, even though the basic algorithm, the basic version has only 2/3 success probability, we are going to see that by doing this trick, we can boost up the success probability to 1 minus delta. Meaning, so we have this bound, right, with 1 minus delta probability. Okay, you cannot change this precision. However, you can boost up success probability by repeating the same algorithm many times. This is using median tree. Okay, this is why it's true. So I get this. I give you some sketch here. I think it's kind of good exercise, but see. Okay, what do we do? So I'm going to draw some picture here because I think it's kind of a maybe some. Right. So let's call this delta, right? So it's F A minus delta, F A plus delta. Okay, this is a true value, right? But it's kind of distant estimation. So if my estimation falls into this range, I'll be happy. Okay, but the thing is that now I'm going to have like this T estimates, right? So like think of this like some like a line here, right? So whenever I estimate, maybe I'm lucky, I'm unlucky, or happy, unlucky, right? So I'm going to have some like some estimates in the range, some are out of the range. Okay, and then what I want is that the median of this, right? What's the chance of the median of this fall in this range? If that probability is 1 minus delta, I'm done, right? So let's call this like this L, M, R. What is L? L is the number of estimates, right? Less than FA minus delta, right? This is like underestimate. How many times I underestimate? Okay, likewise R means the number of estimates greater than FA plus delta I. This is the kind of how many times I overestimate. Okay? Then what I want to know here, I want to see bound the median is bad. Okay, median is out of this range, right? Okay, if median is out of this range, median is not out of this range, for that event to happen, so we must have at least, we must have at least like a majority of elements, right? Estimate should appear here or that, right? So this means that is T. So out of T, so we have too many underestimates or too many overestimates, right? You can have a union bound, right? Good. Then we just need to bound this, right? And what's the probability that L is more than T over 2, right? What I know is that, okay, see, here, like what is right? Because I know that with this Bayesian algorithm, I'm successful with the probability 2/3, right? So it'll be more than 2/3, right? If you count it in this M, right? How many times I'm locked here? It'll be more than 2/3 T. So this means that U of L will be less than 1/3 of L T. Okay. Then what is the probability that, okay, given that the expectation is T over 3 and most y, what's the probability that the L is have a too high value, right? So you can use channel bounds here, because it's like a random point. Okay, so if I just throw a ball, okay, so I'm with 2/3 chance I'm good. Otherwise, I can be here, right? But I know that here I expect to have like at most T over 3 balls, right? But I was unlucky. I have too many balls, right? So this you can, because we are learning, we are learning this T copies of the algorithm using completely independent hash functions. They'll be completely independent. So you can use channel bounds, and you can show this 1 minus delta property guarantee. That's sketch. Does it make sense? Here there's a subtle thing, right? So here I was able to use a channel bounds because these points, right, where these points lie, they are completely independent. Okay, these 2 points, where these 2 points lie, I mean they don't, these two are completely unrelated, right? Because I'm running T copies of the same algorithm, they're totally independent because I'm choosing completely different hash functions for each copy. Okay, but here I'm careful because when you use hash functions, right, the hash function is not completely random function. It's just it has a limited random, right? This, right? I can only guarantee to have a pairwise independence. That's why I need to talk about this variance and expectation. Okay. Anyway, so that's it. So it remains to show these 2 properties. Super good. Okay, let's take a 10 minutes break and then resume.